All right, just a quick overview on Tech Assignment C. All right, as you can see, it's due midnight before Unit Test 3. All right, 20 points. But this time we're going to be using Geogebra rather than Desmos. So I have geogebra.org opened up here. You're going to want to create an account and log in, but let me take you to the assignment. All right, so go to geogebra.org, create an account. You can link it just like Desmos. You can link it with Google or whatever you prefer. I mean, there's a bunch of different options, but yeah, you can explore that. If you have any questions, just reach out to me. All right. Obviously, the watching the video part is irrelevant because this is the video. If you're here, you've already gone down that road. We're going to go to geogebra.org/graphing. So once you've created an account, you can go to, well, there's actually a few different calculators that work, but if you go to geogebra.org/graphing, that'll get the job done. So if you're ever in doubt, it's the graphing calculator one, but if you're ever in doubt, just type it into the address bar. All right, and so there's your graphing calculator. All right, so we're going to create sliders. We're going to create some functions and so on. All right, so I have the guided example here. Create a slider for constant C. To do this, just type in the letter C and hit enter, and you'll have a slider. You can manipulate the parameters if you want and make it go negative whatever to whatever. I'll go negative 10 to 10, going by, you leave it blank to be as precise as possible, but I'll go by quarter units. All right, then just click into the next field and you'll see that it is not at all going by quarter units. I don't know why I didn't do that. 0.25, let's try that again. Maybe it didn't accept it. Oh, because I clicked out of it. You want to hit enter after you make your selection. All right, so that was my bad. All right, so you'll be assigned a transcendental function just like you were in the last couple of assignments. I'm going to use e to the x as an example, so I'm going to type that in as f of x equals e raised to the x. Just do a shift 6 for the caret, or to raise to an exponent. I do that just so I don't have to go looking in the keyboard. Hit enter, lock it in, you got your e to the x function. All right, and the slider, we'll get to the purpose behind that in a minute. All right. So we're going to find the first, second, and third derivatives, and fourth, sorry. I only noted the third here for some reason. So g of x, we're going to define as f prime. It'll just say n deriv, so it knows the notation. Right? So it just has a different way of representing the notation in GeoGebra. All right, so h of x. I mean, you could type in n deriv of f if you want, but this is just a little bit more user-friendly. H of x is equal to the derivative of g, I of x is equal to the derivative of h. So we have f, the first derivative, which is g, the second derivative, which is h, the third derivative, which is I, so we would need the fourth derivative, which would be j. So j of x. You just don't want to call it j, you don't want to call it I for the third derivative and j for the fourth derivative, because it'll get confused and think you're talking about the imaginary unit I and the imaginary unit j. I'm sorry, the vector j. Imaginary unit I, vector j. So imaginary unit j. What a world. All right, so I prime of x. All right. So you can see here, I kind of bounce back and forth. You can type it in as I prime or I prime of x. All right, so we have those functions typed in. Now we're going to put in the Taylor polynomial. So all of this has to get into Geogebra, so that'll be fun. So if you want, just for the sake of keeping things organized, you can use the notation. You hit that little plus, you could put a little text item here. And if you want to do that, you can just say, for example, the first term. It's not a requirement. It's just, for organization, it might be helpful because, we're using a lot of different variables in place of f and f prime and all that. So it could be pretty easy to get things messed up here. All right. So the first term of the Taylor polynomial that we're going to call to order, or we're going to call into play here, is f of c. All right. So, but I want that to be stored in as a value, so I'm going to call that value a. So I'm going to call my first term a equals f of c. And you might be like, well, what c are you talking about? Way back in the beginning, we created a slider for c. All right, so you see when c is whatever the slider is on, I'll look up at that in a second, it's 0.135. Let's see if it's at -2, but let's say if I move it to just a nice, clean, convenient 0, it's at 1, which is what you would expect because e to the 0th is equal to 1. All right. So then the second term of my Taylor polynomial, you just type in quotes if you want, but it's just kind of nicer, I think, if you go text. It knows that you're dealing with text and you're ready to rock and roll there. All right, so this is my second term. Okay, and so my second term is going to be, if you look at the Taylor polynomial, f prime of c, which we just called, oh, well, actually, we haven't called it anything yet. No, strike that from the record. F prime of c times x minus c. All right, so the f prime is really g. All right, so we're gonna put that in as g of c instead of f prime of c. All right, so my second term is really g of c times x minus c. All right, and so this is, we have our first term, which is a. This would be our, really not our second term, it'll be our first two terms. All right, so because I also want the first term along for the ride. I want to kind of build upon the previous one. So instead of saying f of c plus my second term, I'm going to take a plus, now I have g of c times x minus c. All right, now again, because I want to be able to use that as a building block for the next part of the Taylor polynomial, I'm going to call that just some other function, just sort of a placeholder. We'll call it p of x. Just kind of work to the, different part of the alphabet. All right, so the way this is interpreted by Geogebra is saying 1 plus the numerical derivative of f, all right, that's what we call g, times x, but that's only x because we let c be equal to 0. So let's slide, oops, kind of took off on me. Slide this over to a 1, and now you see it's an x minus 1. All right, so my first three terms of the Taylor polynomial, you see, what did I forget to do? I forgot to put it in as a as text. All right, so it assumed variables for each thing that wasn't already defined. So first three terms. Okay, and it did it again. What's going on here? What's going on here? I officially confused Geogebra and myself. Let's see. All right, I fixed it up. You know, sometimes, and you'll find this with GeoGebra more than Desmos, definitely, is that when you make a mistake, it kind of stores that mistake and it assumes that mistake as something true, and it kind of tries to hold you to that mistake. So no matter how much you try to correct it, there's always going to be that resistance on GeoGebra's part to allow you to make a correction to a mistake. So sometimes you just have to wipe it out and do it again. All right. Speaking of getting things wiped out, let me stop for a second here and save this so that, and I'll walk you through the whole thing about share links and stuff like that. But let me just do a quick save here. Click on the little menu bar, go to save, call it something. I'm going to call it Tech Assignment C. Can Summer 2019, geez. Now I'm just making stuff up. Very important, in the little drop down thing here, you might want to call it private. You know, like your tendencies might be to call it that because you don't want the whole world to see it. You won't be able to create a share link if you don't have it set to shared. So don't put it on private, put it to shared. Have it, you know, give you that nice little reminder that it's saved successfully, so you're good. You won't lose all your work. And then when it's time to create a share link, you'll be able to copy it right out of here. All right, but make sure it's set to share. I'll go over that again at the end, but I just wanted to take a minute because with GeoGebra, if you don't save your work and it crashes, you'll lose your work. With Desmos, it was a little bit more forgiving. All right, so for the first three terms, well, our first two terms is stored as P of X. So now I just got to tack on the third term, all right, which is my second derivative divided by 2 factorial, all right? So plus my second derivative, which is h of x, oops, all right, oh, sorry, h of c, because we're doing it at the constant, divided by 2 factorials. So I'm going to tuck in a little division bar there. Just hit the division bar in front of the h of c. 1 over 2 factorial. Just type in the exclamation point or go into the little keyboard here and do it. All right. Times. Now we're putting in x minus c. So this time it really is an x minus c raised to the second power. Now I'm going to hit enter here. Oh, before I do that, I'm going to save this as r of x. I'm sorry, q of p, q, r, whole alphabet thing. All right, so now what I want to draw your attention to is in the graph, if you look carefully, because the c value that I have going on here, and there's a lot of stuff that we typed in so far, but it's at 1. If you look at 1, and start making a comparison between P, Q, and the original function. So I can actually turn off F, G, because those are just building blocks of my Taylor polynomial, all those derivatives that we computed. Get those out of the way. Just look at the P and the Q. All right. All right, so I want to compare that to my original function f. Hopefully, if you do a quick comparison, you start to make the realization that when you incorporate more terms, you're getting something in terms of your graph that's more and more of an accurate representative of the f of x. All right, so for a very limited interval, we could approximate the original function f of x using p of x. All right, just this guy here. But for a wider interval, see, it's almost indistinguishable. I mean, when we move out, it starts deviating more substantially. But for a wider interval, we're able to approximate f of x using q of x. All right, so q of x is a better model there. All right, so you see what happened here? You see that where it says furs and 3 and all that? That's when I accidentally typed in the first 3 terms. It created sliders for each of those. So let me just get rid of those because those shouldn't be there. All right, so now I need my first 4 terms. Oh, look at me about to do the exact same thing again. All right, so first 4 terms. So now I'm going to create a function r of x, which is going to start off with q of x, which is everything that we just computed, but then the next term, which is we had our second derivative, so now it's the third derivative. Sorry, there should be a plus sign. 1 divided by 3 factorial. All right. Then we incorporate the third derivative, which is I of x, so I of c, times x minus c. We did second power previously, so now we're up to the third power. Lock it in. And now I'm just going to do a quick comparison between q and r. All right, so now let me turn off q and just do a quick comparison between the original function and my new Taylor polynomial. I think it's pretty easy to see that this is holding on to the function f of x for a longer period or a longer interval. All right, so it's becoming a better approximator of that function. So let me get the first 5 terms. So we'll need the 5th term, but so I didn't put it in here on the document because my directions up here said find the first, second, third, 4th derivatives. So we need the next one. All right. So where did I leave off? Well, I used r of x. So s of x is going to be equal to r of x, so r of c, plus, I'm sorry, not r of x. Is it obvious yet that I'm doing this at 2:30 in the morning? We'll find out. So 1 divided by 4 factorial, then j of c times x minus c. Now it's going to be raised to the 4th power. All right. So that's my first 5 terms. And it's the Geogebra translation of it is kind of a mess at the bottom, but we can live with it. And you can see, we're up to a 4th degree polynomial now. It's oscillating back and forth between something that's very much like a cubic function and very much like a quadratic. Now, cubic and quadratic. So now finding the deviation between these two functions is kind of tricky, but what we're looking for really is which one holds on the longest. All right, so if I bring it into when they start separating out, it looks like the orange one is hanging on to the green one a little bit longer on the high side in terms of the x values than the red. And in fact, it's pulling away, but not as rapidly as the red one is. All right, when we go on the low side, it looks like they kind of both pull away at the same rate. Maybe the orange one seems to hold on a little bit more, but then once it gets to its turning point, then they really both deviates substantially. All right. So what you're going to do is that, all right? Just you have different functions to work with. And the idea is that you can find or develop a series of Taylor polynomials that you can use to come up with approximations depending on a variety of c-values. So I can move my c-values, and if I move it around, you can see where or what interval the approximate functions, the Taylor polynomials, will hang on to the original function. And if we can incorporate infinitely many of those terms, then we would have an exact approximation of a transcendental function, which, when you think about things like limits and derivatives and antiderivatives, those are the more complicated types of functions. But when you think about a polynomial function, those are nice and easy, right? So that's the idea, to be able to convert from transcendental, like your exponentials, your logs, and other trig functions and stuff like that, into something that's definitely polynomial based. So you go ahead and save it. All right, you give it a name, like I said before. Absolutely make sure that you've selected shared. And then once you do that, you go to shared and copy your share link, and you pop that right into Blackboard. Now, one last thing, a very minor detail. At the end of it, once you've done all your work, just the only thing I really need to see is the last polynomial. All right. So if this polynomial and your original function seem to be one approximates the other over a significant interval, then you're in good shape. You'll be looking at full credit.